Urban heat island effect is intensifying across Los Angeles County as dense development, industrial corridors, dark roofing, and expansive asphalt surfaces absorb and store solar radiation throughout the day. This heat is slowly released at night, preventing natural cooling and creating persistent hotspots. Neighborhoods with low tree canopy and high impervious surface coverage experience the greatest thermal stress, and these areas often overlap with communities that are already socially vulnerable. ShadeLA was developed to identify where shade is lacking, quantify the cooling gap, and simulate targeted interventions that measurably reduce urban heat. The project begins with NASA EcoStress land surface temperature data, which provides high-resolution thermal imagery at approximately 70 meters per pixel. These datasets are integrated to generate a priority score for each census tract, identifying which neighborhoods would benefit most from shade interventions and how much cooling potential exists. The core of ShadeLA is the integration of this spatial analysis into a digital twin workflow. After processing EcoStress heat maps in GIS, we created interactive maps using ArcGIS Online that visualize urban heat exposure, existing canopy coverage, impervious surfaces, and priority areas. These maps are embedded into the ShadeLA project website, which serves as a centralized dashboard for spatial analysis and digital twin visualization. From GIS, the workflow moves into three-dimensional modeling. Using Rhino, we built 3D street geometries and shading structures within targeted areas. Rhino provides the spatial framework for modeling sidewalks, building edges, and proposed canopy systems. Within Rhino, Grasshopper is used for parametric modeling, enabling adjustable canopy geometries, spacing strategies, and structural configurations. This allows rapid iteration and scenario comparison. Environmental performance is evaluated using Ladybug tools inside Grasshopper. Ladybug analyzes solar radiation, direct sun hours, and thermal comfort metrics such as UTCI directly on the modeled sidewalk geometry. This allows us to measure how shade coverage changes microclimate conditions and reduces heat exposure. The workflow extends into Unreal Engine, where the geometry and data layers are visualized in immersive form. In Unreal, we simulate shadow movement, visualize temperature gradients, and compare before and after intervention scenarios. This transforms the digital twin into a predictive planning tool, allowing designers and planners to test solutions before implementation. To support the design phase, we developed a Shade Solutions library integrated into the ShadeLA platform. This interface functions as a searchable dataset of shade typologies that can be filtered by category, material, technological integration, and ideal placement. Each solution includes a visual model and descriptive metadata to help designers compare strategies quickly. ShadeLA transforms urban heat island mitigation into a measurable, data-driven design strategy. By integrating NASA satellite data, GIS mapping, parametric modeling in Grasshopper, environmental simulation with Ladybug, visualization in Unreal Engine, and a centralized web dashboard, the project establishes a unified digital twin ecosystem. Heat becomes a quantifiable design parameter, and shade becomes a modeled, optimized, and performance-based urban solution.